Hey everybody, and welcome to a brief video on section 3.11, which is about hyperbolic functions. So I'm sorry I had to cancel class so abruptly. It's just sometimes your kid's daycare calls you 10 minutes before class, and she scares the bejesus out of you with a little health crisis. But anyway, this section is short in the book, and it's also short in what we will do. We aren't going to do everything the book does. So let me just briefly outline for you what you need to know from section 3.11 in order to do your homework and know what the physicists want you to know and things like that. So this brief video covers 3 questions. Why would we study these functions? What are these functions? And, of course, what are their derivatives? This third question here is why we're doing this in a calculus course. We want to know about their rates of change. Here is your learning goal for this section. By the end of this video, you should be able to do what we have been doing. Take derivatives, answer questions about rates of change, answer questions about slopes of tangent lines. The same thing we've been doing for a month now, but now you should be able to do those questions with functions that involve these hyperbolic trig guys. So we're just adding more functions to our toolkit that we can trot out and take derivatives of. So the first question, why study these functions? Because they have applications mostly in physics and engineering. Science is a pretty generic term, isn't it? But physics is what I have in mind. So these functions occur whenever an entity such as light, velocity, electricity, radioactivity is gradually absorbed or extinguished. The decay can be represented by one of these functions. Another example, if you take a rope, or maybe a power line, if you like that visual, you fix the two ends and let the rope hang, then gravity will force it down into the shape of a hyperbolic cosine curve, a hyperbolic function. They also show up in places like relativity theory, which you will see in your group work problems. So they show up in physics, that's why we're doing these now. What are these functions? Let me define them for you. Here is hyperbolic sine. It's defined as a difference of exponential functions. Here is hyperbolic cosine. So the little h right here is just for hyperbolic. So this isn't sine we're talking about. This is hyperbolic sine, which is different. Hyperbolic sine is defined like this: e to the x minus e to the negative x, all divided by 2. And you can split that fraction into 2 pieces if you want to. E to the x cut in half minus e to the negative x cut in half. Hyperbolic cosine is defined the same way, except that minus is turned into a plus. Okay, so hyperbolic sine and hyperbolic cosine are both kind of mouthfuls. So people call this sinh. So S-I-N-H, right? Sinh. And people call this cosh. So this is sinh of x. This is cosh of x. And the other 4 hyperbolic trig functions are defined just like you would expect them to be. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine, just like normal tangent is normal sine over normal cosine. Hyperbolic cotangent is hyperbolic cosine divided by hyperbolic sine, just like normal cotangent is normal cosine over normal sine. You get the idea, right? Secant and cosecant are also defined as you would expect. So here are the 6 hyperbolic trig functions. And by the way, if you're wondering about the word hyperbolic, essentially there are hyperbolas embedded in the theory of these guys. So it's not sort of an arbitrary choice of word. It's not important for us how hyperbolas play a role. This is just how they're defined. Here's a random piece of information for you. You will all recall that cosine squared plus sine squared equals 1. So you might think that hyperbolic cosine squared plus hyperbolic sine squared equals 1 as well. Unfortunately, that's not true, but what is true is if you change that plus to a minus, you get something true. This will be useful in at least one of your group work problems, and it's also probably useful in the homework. So keep this in mind. You can always use this, that cosh squared minus sinh squared is 1. And from this identity, you can derive other ones if you feel like it. So for example, if you divide both sides of this by cosh squared, then you get a 1 right here, right? Cosh squared divided by itself. Here you get sinh divided by cosh squared, which is hyperbolic tangent squared. And over here you get 1 divided by cosh squared, which is called hyperbolic secant squared. So anyway, once you have one identity, you can usually derive others from it if you want to. So this is also true. Okay, derivatives. Let's take the derivative of hyperbolic sine. So if I gave this problem to you cold and I said, I'm not going to show you what this derivative is. Okay, I'm not going to tell you what it is. It's worth thinking about what would you do. And in class, of course, I would just make you do it. I would make you figure out how to differentiate sinh. But since we're not in class, and since I can't force you to do anything through the computer screen, let me just show you how that goes. So sinh is just defined like this. So the derivative of sinh is the derivative of e to the x over 2 minus e to the negative x over 2. And these are perfectly friendly guys to differentiate. This is just 1/2 times e to the x right here. I don't know why it keeps highlighting too much, whatever. 1/2 e to the x, which doesn't change when you differentiate it. The derivative of e to the x is itself. This guy is 1/2 e to the negative x. So the chain rule says if you want to differentiate e to the negative x, you do e to the negative x, you leave the e to the stuff alone, and then you multiply by the derivative of what was inside. In this case, negative x. The derivative of negative x is -1. So notice that's why this minus changes to a plus, because you bring this negative sign down as a coefficient of -x. So you get a negative. So again, to derive this little guy here, this piece here, e to the negative x over 2, it is the chain rule. It's just like differentiating e to the 17x or something, things we've done before. So anyway, you end up with this, but this, if you remember previous slides, should look familiar to you. It is hyperbolic cosine, which we kind of should have guessed, shouldn't we? The derivative of sine is cosine, so the derivative of hyperbolic sine should probably be hyperbolic cosine, and it is. What about the derivative of cosh, of hyperbolic cosine? Again, if we were in class, I would ask you what you think about this. You would most likely say the derivative should be negative hyperbolic sine, because the derivative of normal cosine is negative normal sine, right? That doesn't quite work out to be the case though, so the analogy stops there. To find this guy's derivative, we just again go back to the definition. It's just a sum of exponentials. And again, e to the x over 2 is just 1/2 times e to the x. That does not change when you differentiate. And again, e to the negative x, the derivative of that is negative e to the negative x. So now that minus becomes a plus, that plus becomes a minus. And again, if you think about what this is, you've seen this before on a previous slide. That's just hyperbolic sine. So the derivative of cosh is not negative sinh. You actually don't pick up a negative sign. The derivative of cosh is just sinh. So it's almost like the normal trig things, but it's not completely analogous. You do lose a negative sign here. What about the other guys? Again, if we were in class, I would say, how would you find the derivative of hyperbolic secant? You all can do this. In particular, if you remember back to when we found the derivative of normal secant, what we did was we said, well, you can write secant as a fraction, can't you? 1 over cosine, or in this case, 1 over hyperbolic cosine. And we all know how to take derivatives of fractions, don't we? We can just use the quotient rule. So using that, you do the bottom squared down here, you put the bottom right here. Derivative of the top is the derivative of 1, which is 0. And then you do minus the top function, which is 1, and multiply by the derivative of the bottom function, which again, the derivative of hyperbolic cosine is just hyperbolic sine, not negative hyperbolic sine. So there's just a sinh right here. And there you go. That's the derivative. You simplify it a little bit. 0 times anything is 0. And then just like we did with the regular trig functions, we can split this fraction into two pieces. And I'm sorry, this is a typo right here. This negative should not be there. Just this negative here. So sorry, this negative, scratch it out. Like take a pen to your computer screen and scratch it. Okay, so with just a single negative there, you have sinh over cosh, which is tanh, I guess, hyperbolic tangent. And you have 1 over cosh, which is hyperbolic secant. So the derivative of secant is itself times tangent, and you pick up a negative sign. So again, this is close to the normal trig stuff. Remember, the derivative of just normal secant is tangent times secant. So again, the analogy isn't perfect here, but it's basically the same. You just pick up a negative sign when you're dealing with the hyperbolic secant. So again, you guys can all do this. You might be asked to do it on an exam, maybe on a bonus question if you were to see it, but it's just a straightforward quotient rule kind of thing. So these two we've fully explained. This one we've also fully explained. The other three you can get from a quotient rule, because hyperbolic tangent is hyperbolic sine over hyperbolic cosine. So you can just take the derivative of that quotient. Hyperbolic cosecant is just 1 over hyperbolic sine, and the computation will look much like this, and you'll get, where was I? Yeah, you'll get this, negative hyperbolic cosecant times cotangent. So hopefully what you take away from this page is that the hyperbolic trig guys work essentially like the normal trig guys. It's just there are negatives in certain places that there weren't before, and there are negatives missing in places there were before. Like before there was a negative here, now there's not. Before there wasn't a negative here, but now there is. Okay, but otherwise it's basically perfectly analogous. So to finish, let me just give you an example using these guys. So with this in place, you can now do everything we've been doing, can't you? The chain rule and product rule and things still hold, don't they? Derivatives still tell you about rates of change, don't they? Derivatives still tell you about tangent lines, don't they? So you can still answer any question like we've had before. So here's a question that is kind of like what we had before. If I give this to you, and of course if we were in class, I would make you do this at your desk and report back to me after 2 minutes. But since you're not here and I can't talk to you directly, let me just point out to you this is a product, isn't it? Sinh of stuff times cosh of stuff. So we're going to have to use a product rule, but we're going to have a product rule with a couple of chain rules going on inside of it because we have this function inside of a sinh, we have the natural log function inside of a cosh. So let me just point out to you that the derivative of sinh of x plus 1 is cosh of x plus 1 times the derivative of that inside function. This is just the chain rule I'm doing here, right? Take care of the outside function first, and then slap on the derivative of the inside function. But of course, the derivative of x plus 1 is just 1, so we end up with just cosh of x plus 1. And the derivative of cosh of natural log, how do we handle that? Well, we take the derivative of the outside guy, leave the inside alone, and then we multiply by the derivative of the inside guy, which is 1 over x. So using the full product rule and putting these two pieces of information together, we get this. F prime of x is, wait, what did I do here? Okay. I'm not sure why I confused myself. I left the first alone, didn't I? And then I did the derivative of the second, right? That's what this is. So first times derivative of second plus derivative of first, right? Cosh of x plus 1 we already got times second. So there's the product rule in action with my two chain rules inside of that. So that's it for section 3.11. If any of this does not make sense, if the group work problems or the homework give you trouble, please just email me or ask me on Monday. So have a good weekend.